Between Mars and Jupiter lies a secret we are only just beginning to uncover. Our solar system holds an invisible asteroid belt, a vast collection of material hidden in plain sight from our most powerful telescopes. This is not science fiction, but a cutting-edge scientific mystery that challenges everything we think we know about our cosmic neighborhood. You will learn how astronomers found clues to this missing mass and why its discovery could rewrite the history of our solar system. We will explore how an entire structure could remain unseen and what its ghostly presence means for the future of space exploration. What does it feel like to realize we are still mapping the shadows in our own backyard? Most of us carry a mental image of the asteroid belt as a chaotic junkyard swarming with rocks. This classic picture, fueled by countless science fiction films, is both instantly recognizable and almost completely wrong. The reality is far more serene and scientifically profound. Stretching across a colossal void between the orbits of Mars and Jupiter, this is the main belt, a region so vast that its millions of occupants are mostly lonely wanderers. If you were to pilot a ship through its heart, the chance of even seeing another asteroid, let alone colliding with one, would be astronomically small. This is not a crowded demolition derby, but a sprawling, silent frontier. Its story begins with a cosmic what-if. The leading theory suggests this entire region was once destined for greatness, a potential planet that never got the chance to form. In the early solar system, countless small building blocks called planetesimals swirled here, but the immense gravitational pull of the nearby giant Jupiter stirred this cosmic soup with relentless turbulence. These embryonic worlds were thrown into chaotic orbits, colliding with each other too violently to stick together and grow. Instead of coalescing into a single world, they shattered, creating the scattered fragments we see today. Within this sea of rubble are ancient survivors like the dwarf planet Ceres, a spherical world holding nearly a third of the belt's total mass. Alongside it orbit giants like Vesta and Pallas, protoplanets frozen in time that offer a glimpse into that primordial era. They are not just random rocks, they are the unfinished business of our solar system's birth, a fossil record written in rock and ice. So why does this familiar belt hide a deeper secret? Yet the serene emptiness of the main belt held a quiet puzzle. For decades, astronomers meticulously tracked the paths of thousands of asteroids, mapping their endless loops around the Sun. They plotted orbits governed by the predictable gravitational dance of the Sun and the dominant pull of Jupiter, but slowly, a pattern of small inconsistencies began to emerge. Certain families of asteroids seemed to be marching to a different, subtler drumbeat. Their orbits displayed slight, collective peculiarities that the standard models of gravity could not fully explain. It was as if an unseen hand was gently herding them, creating faint patterns in the cosmic dust. Groups like the Hungaria family, nestled close to Mars, or clusters within the central belt, exhibited strange, resonant orbits and unexpected clustering. These were not random deviations. They were the first faint whispers, the initial clues that the gravitational story we thought we knew was incomplete. Something else, something hidden, was exerting its own faint influence on the dance. These faint orbital whispers were the gravitational fingerprints of something unseen. To understand how scientists read these clues, you need to think of gravity not as a simple force, but as a cosmic detective. Every single object with mass, from a star to a speck of dust, creates a tiny dimple in the fabric of space-time. When another object moves nearby, its path is subtly altered by that dimple. Now picture a spacecraft like Dawn, which visited the giants Vesta and Ceres. Its trajectory was plotted with incredible precision, yet as it traveled through the main belt, navigators detected minuscule, unexpected deviations in its path. It was not being pulled off course by the massive asteroids we know, but by countless tiny, unseen sources of gravity. These were the signatures of the hidden population. This phenomenon is called a gravitational anomaly. It is a mismatch between what we expect an object's motion to be based on visible mass and what we actually observe. In the asteroid belt, the observed motion of known asteroids, and even the subtle drift of planets like Mars itself, indicates that there is significantly more mass present than our most powerful surveys have ever spotted. Think of it like sensing a crowd of people in a pitch-black room, not by seeing them, but by feeling the floorboards creak and shift under their collective weight. The invisible structure reveals itself by the way it gently tugs on everything that passes through its domain. This hidden mass is not a single, massive object, but a vast, diffuse collection of material, likely composed of countless dark, carbon-rich asteroids and dusty debris that simply do not reflect enough light for our telescopes to find. They are the ghostly infrastructure of the belt, and their collective gravity is the only thing that gives them away. But if this mass is truly there, woven into the void between the planets, why has it remained so stubbornly invisible for so long? The true nature of this hidden mass may lie in a substance so fine it has eluded our gaze for centuries. Imagine not a belt of boulders, but an immense, diffuse cloud of cosmic dust. This is the dusty veil hypothesis. The space between the known asteroids could be saturated with countless trillions of microscopic particles and pebble-sized fragments, all orbiting the Sun in a vast silent shroud. These particles are the key to their own invisibility. To be seen from Earth, an object must reflect a significant amount of sunlight back toward our telescopes. A large, icy asteroid acts like a brilliant mirror, but a tiny, dark speck of carbon-rich dust is virtually a black hole in space. It absorbs light instead of reflecting it, blending perfectly into the in-sky void. Our most powerful observatories are essentially looking for needles in a haystack by waiting for them to glint. But if the needles are made of soot, they will never gleam. This explains why we can sense the crowd in the dark room by the shifting floor, yet our flashlight reveals nothing. The collective gravitational pull of this immense cloud is undeniable, but its individual components are simply too dark and too small to see. Their presence, however, might be revealed through other senses. Just as you can feel a breeze you cannot see, astronomers are developing new ways to detect this ghostly material. They look for the faint warmth it radiates, or the way it subtly scatters certain types of radiation, creating a faint, ethereal glow that is invisible to our eyes but detectable by specialized instruments. This hidden dust belt is more than just a scientific curiosity. It is a potential time capsule. These dark, carbon-rich particles could be pristine leftovers from the very formation of our solar system, material that has never been heated or processed, preserving secrets from a time before the planets even existed. To see this ghostly dust, astronomers had to stop looking with light and start feeling for heat. Even the coldest objects in space, drifting in the profound chill of the void, retain a faint whisper of warmth. This thermal energy radiates outward as infrared light, a form of radiation invisible to our eyes but detectable as heat. Think of it this way: you can sense the warmth of a person standing near you in a pitch-black room long before you can see them. This exact principle is how we are beginning to map the invisible asteroid belt. By switching from optical telescopes to infrared observatories, scientists turned their gaze to the thermal glow of deep space. Space-based telescopes like NASA's Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, known as WISE, became our heat-sensitive eyes on the cosmos. They scanned the entire sky, not looking for reflected sunlight, but for the faint, inherent warmth emanating from every object. When they turned their infrared gaze toward the main belt, the data revealed something astonishing. Beyond the expected heat signatures from the known large asteroids, there was a persistent, diffuse glow. It was not coming from any single point, but was spread across vast stretches of space like a cosmic mirage. This pervasive warmth was the collective body heat of countless trillions of unseen particles. This was the confirmation of the dusty veil, a faint infrared signature revealing a reservoir of material an order of magnitude more massive than anyone had previously estimated. The belt was not mostly empty, it was filled with a sea of fine, dark dust that had been hiding in the shadows all along. This discovery forces a profound shift in our understanding. The asteroid belt is not just a collection of lonely rocks, but a dynamic system where this invisible cloud of dust interacts constantly with the asteroids we can see. But what does this hidden ocean of material mean for the very formation of our solar system? This discovery of hidden mass inevitably leads our minds toward the grandest cosmic mystery of all. Could this invisible structure be a small, concentrated knot of dark matter? To even consider this, we need to understand what dark matter is. Think of the universe's gravity as a recipe. When we look at a galaxy, we can calculate how much gravity it needs to hold itself together, to keep its stars from flying apart. But when we add up all the gravity from every star, every planet, and every speck of dust we can see, the total is far too little. There is not enough visible mass to account for the powerful gravitational glue holding the cosmos together. The rest of that gravity, the vast majority of it, must come from something we cannot see. This missing ingredient is what we call dark matter. It does not absorb, reflect, or emit any light, making it completely invisible to every kind of telescope we have. We only know it exists because of its immense gravitational pull on the scale of entire galaxies. So, if dark matter's signature is its gravity, and we have detected unexplained gravity in the asteroid belt, is this the same phenomenon on a smaller scale? The answer, fascinatingly, is almost certainly no. Astronomers have largely ruled out this tantalizing possibility. The reason lies in the distribution and behavior of dark matter. We believe it forms an immense diffuse halo that envelops entire galaxies like a ghostly sphere. Its effects are felt across distances of hundreds of thousands of light years. The subtle, localized tug we see in the asteroid belt is not the right fingerprint for this cosmic phantom. The gravitational anomalies here are better explained by something far more ordinary, yet still hidden baryonic matter. That is the scientific term for the regular stuff you and I are made of, the protons and neutrons that constitute all known rocks, ice, and dust. The evidence points not to an exotic new form of matter, but to a colossal amount of perfectly normal, ancient material that is simply too dark and spread out for our telescopes to spot. This distinction is crucial. It means the secret of the asteroid belt is not a portal into the dark universe, but a reflection of our own solar system's dusty, unformed past, hidden in a shroud of its own making. This hidden debris field forces us to rewrite the very first chapters of our solar system's story. The sheer amount of invisible material points toward a past far more tumultuous than our previous models suggested. We thought we understood the belt's creation, a story of gentle growth interrupted by Jupiter's bullying gravity. But the existence of this colossal dust cloud hints at something far more dramatic. Imagine a single, massive world in the making, a primordial planetesimal not just the size of Ceres, but perhaps even larger than Mars. This was no mere building block, but a nearly finished world, an almost planet that once orbited peacefully in the young solar system. Then catastrophe struck. The leading theory now suggests this protoplanet did not simply fail to form, it was utterly obliterated. A collision of unimaginable force, an event so violent it makes every asteroid impact in Earth's history look like a gentle tap shattered this world to its core. The largest chunks became the asteroids we know, like Vesta and Ceres, but the majority of its substance was pulverized into a fine, dark mist of dust and rubble, the very material that now forms this invisible veil. This apocalyptic event would have been far more than a single crash. It would have been a chain reaction of destruction, with fragments smashing into each other for millions of years. grinding themselves down into the fine powder we can only detect by its gravity and its faint warmth. Why would this debris settle into a different, hidden structure? The physics of such a colossal breakup provide the answer. When an object is shattered, the resulting fragments do not all behave the same way. The larger pieces retain more momentum and are more susceptible to the gravitational influences of Jupiter, settling into the orbital plane we recognize as the main belt. But the finest dust, the microscopic particles born from the most intense grinding, are subject to different forces. The gentle but relentless pressure of sunlight itself, a force known as radiation pressure, can slowly push these tiny particles over immense spans of time. This solar breeze could have shepherded the finest dust into a slightly different orbital inclination, creating a vast, diffuse cloud that wraps around the main belt like a ghostly blanket on a slightly tilted angle, forever hiding it from our direct view. This means the asteroid belt is not merely a collection of failed planets, but the graveyard of a single, shattered world. Jupiter's shadow looms large over this entire mystery. The gas giant is more than just a distant neighbor. It is the grand architect of the belt's very existence, a colossal force of both creation and chaos. Its immense gravity, which spans hundreds of millions of miles, acts like a cosmic sculptor, constantly shaping and rearranging the material between it and Mars. We see its most famous handiwork in the Kirkwood gaps. These are narrow, empty lanes within the main belt where virtually no asteroids are found. They are not random voids, but precise gravitational dead zones. An asteroid orbiting within one of these gaps would complete its journey around the Sun in a simple fraction of Jupiter's own orbital period. For instance, an asteroid might circle the Sun 3 times for every one of Jupiter's orbits. This creates a rhythmic, repeating gravitational tug from the giant planet. Like pushing a child on a swing at just the right moment, these periodic nudges accumulate over time, not stabilizing the orbit but destabilizing it. The asteroid is gradually pumped with energy until it is flung onto an entirely new path, ejected from the belt altogether. Jupiter essentially clears its own resonant highways, creating these striking patterns of nothingness. But if Jupiter's gravity can so effectively clear out larger rocks, how could it possibly be responsible for hiding an entire cloud of dust? The answer lies in a more subtle, almost gentle aspect of its power. For the finest particles, Jupiter's influence changes from a disruptive force to a shepherding one. While large asteroids are vulnerable to those resonant kicks, microscopic dust particles are governed by a different set of rules. They are so small and lightweight that the steady pressure of sunlight itself constantly pushes on them, a force that is negligible for a mountain-sized rock but significant for a speck of dust. This solar pressure wants to blow the fine dust away, to disperse it across the solar system. But here, Jupiter's gravity steps in not as a wrecking ball, but as a cosmic sheepdog. The giant planet's gravitational field can create stable zones, pockets of space where its subtle, persistent pull counteracts the solar breeze. In these regions, the tiny particles become trapped. They are herded into a stable, hidden configuration, a vast, diffuse ring that is gravitationally bound to Jupiter's rhythm yet optically elusive to our telescopes. This shepherded belt of fine material does not occupy the same precise plane as the larger asteroids. It is a tilted, puffed-up cloud, a structure that exists only because of the delicate balance between the push of sunlight and the guiding hand of a giant. So the very same force that prevented a planet from forming and that clears gaps in the rock belt also acts as the guardian of the belt's deepest secret, corralling the ghostly dust and keeping it hidden in plain sight. What other invisible structures might be hiding within the subtle gravitational folds of our solar system? So what shape does this ghostly structure take? The faint infrared glow and gravitational tugs tell us something is there, but they do not immediately reveal its architecture. Scientists are now piecing together several compelling blueprints for this hidden belt. The first and simplest idea is that of a vast, uniform cloud. In this model, the fine dust is spread evenly throughout the entire volume of the main belt, like a thin, cosmic fog that has settled into every crevice of space between Mars and Jupiter. It would be a diffuse envelope, gently thickening the void around every known asteroid without forming any distinct patterns of its own. This would be the most straightforward outcome of a long history of grinding collisions, a fine powder that has simply never settled. Yet, the subtle orbital quirks of some asteroid families suggest the hidden mass might not be so uniformly distributed. This leads to a second, more intricate possibility: dense, narrow rings of dust. We are accustomed to the brilliant, icy rings of Saturn, but imagine rings made of the darkest charcoal, absorbing light instead of reflecting it. Such rings could form from the debris of a single, recent large breakup, or they could be trapped within stable gravitational resonances with Jupiter, much finer and more concentrated versions of the Kirkwood gaps, but filled with dust instead of empty space. A single, dense ring would create a very specific and powerful gravitational signature, a rhythmic pull on anything passing through it. Then there is the most geometrically elegant hypothesis: a tilted torus. A torus is essentially a donut shape, and this model suggests the invisible material is not in the same flat plane as the rest of the solar system. Instead, it orbits at a slight angle, a puffed-up, warped ring that encircles the Sun. This would brilliantly explain why our telescopes have missed it. Our planetary system is largely flat, like a spinning vinyl record, and our observations are naturally biased toward that plane. If this dust belt is tilted, we are never looking at a clean cross-section of it. We are always seeing it at an oblique angle, its material spread thinly across our line of sight and thus remaining invisible. Each of these hypothetical shapes tells a different story about the belt's violent origins and its dynamic present, a cosmic puzzle where the very geometry of the hidden matter holds the key to a forgotten history. The composition of this ghostly dust is the final piece of the puzzle, a key that could unlock its true origin. Is this hidden mass made of the darkest, most ancient stuff in the solar system, or is it the shattered remains of a specific, long-lost world? The leading suspect is carbonaceous material. Think of a lump of cosmic charcoal, blacker than coal and just as reluctant to reflect light. These carbon-rich asteroids, known as C-types, are some of the most primitive objects we know, time capsules from the solar system's earliest days. If the invisible veil is primarily made of this stuff, it would mean we are looking at a preserved reservoir of the original building blocks of planets, material that has been hiding in the shadows for 4.5 billion years. Its darkness would be the very reason for its invisibility, a perfect camouflage against the black of space. But there is another compelling possibility. The dust could be rich in silicates and metals, the stuff of rocky asteroids and metallic cores. This would paint a very different picture. Such a composition would point directly to a history of immense violence, the grinding down of a differentiated body. Imagine a protoplanet that had actually begun to form a metallic core and a rocky mantle, much like Earth did before it was blasted apart. The resulting debris field would be a mixed cloud of shattered rock and metal fragments. Finding this signature in the dust would be like discovering the forensic evidence of a cosmic murder, confirming the catastrophic destruction of a nearly formed world. So how do we read the signature of this phantom material without ever touching a single grain? Astronomers are turning to the language of light, or more precisely, the absence of it. By studying how this dust cloud absorbs and scatters specific wavelengths of light from distant stars and other celestial objects, they can infer its chemical makeup. It is like analyzing the color of smoke to determine what is burning. Each material, whether dark carbon or reflective metal, leaves a unique fingerprint on the light that passes through it. Decoding this faint signal will tell us if we are staring at the primordial crumbs of the solar system or the scattered ashes of a broken planet. This unseen cloud of dust forces a critical question for our future in space. Could this hidden material pose a silent, unexpected danger to our spacecraft? The answer lies in the difference between a cannonball and a shotgun blast. The known asteroids, those mountains of rock, are easy to track and avoid. We can plot a course through the main belt with near certainty of never encountering one. The true, constant hazard has always been the tiny, unseen population of millimeter-sized particles, the natural background dust of deep space. Now, we must consider that this background population might be far denser than our models assumed. A single particle of this dust, smaller than a grain of sand, carries a devastating punch when it strikes at speeds tens of times faster than a bullet. It is not the size, but the velocity that creates the threat. For a robotic probe, an impact could pierce a fuel line, crack a viewport, or disable a critical sensor. For a future crewed mission, such a puncture could be catastrophic. Our current spacecraft shielding is designed with this known risk in mind, using layers of material like Kevlar and Nextel that act as a bulletproof vest, vaporizing tiny particles before they can penetrate the inner hull. But if the density of this fine dust is an order of magnitude higher than we thought, our current shielding might be like wearing a raincoat in a hurricane. It is a calculated risk that may need to be recalculated. This does not mean the belt is an impenetrable barrier, but it does mean our maps are incomplete. Future missions, especially those destined for Jupiter and beyond, will need updated hazard models that account for this invisible veil. Ensuring safe passage is not about avoiding a few large rocks, but about reinforcing our ships against a potential storm of microscopic shrapnel, the lingering echo of a primordial collision. The invisible belt reveals its secrets not through a telescope, but through lines of code. To understand how such a ghostly structure could form and persist, astrophysicists turn to the immense power of supercomputers. They build digital universes, crafting what are known as n-body simulations. The n stands for the number of particles, and in this case, that number can soar into the millions. Each of these digital particles represents a chunk of rock, a cloud of dust, or a massive asteroid, and each one is programmed with its own set of physical properties, and most importantly, its own gravity. Every single particle exerts a tiny gravitational pull on every other particle in the simulation. Calculating these mutual interactions for millions of objects over billions of virtual years is a task of almost unimaginable complexity, one that requires the raw processing power of the world's most advanced computers. These are not simple animations, they are rigorous mathematical experiments that play out the history of the solar system in fast forward. Scientists can program the simulation with a specific starting condition, such as a single, massive protoplanet orbiting between Mars and Jupiter. Then, with a digital nudge, they can shatter it. They watch as the fragments collide, grind against each other, and slowly spread out, their orbits shaped by the relentless gravitational tides of a virtual Jupiter and the gentle, constant pressure of simulated sunlight. The question is, does the resulting debris field, after billions of years of simulated evolution, look like the hidden structure we detect today? Does it form a uniform cloud, a tilted torus, or a series of dense, dark rings? By running these scenarios thousands of times with slightly different initial parameters, the simulations act as a cosmic filter. They reveal which violent pasts are plausible and which are physically impossible. The most powerful outcome of these digital laboratories is their predictive power. A successful simulation does more than just recreate what we think we see, it tells us where to look next. It can predict that the strongest gravitational signature of the hidden belt should be found in a specific orbital resonance zone, or that the most intense infrared glow should emanate from a particular patch of sky, tilted at a precise angle to the ecliptic. It gives astronomers a treasure map, pointing our most sensitive instruments toward the most likely hiding spots of this cosmic phantom. The hunt for this cosmic phantom is accelerating with a new generation of eyes. Our tools are evolving from mere telescopes to gravitational detectives, and the most powerful of them all is already in space. The James Webb Space Telescope represents a quantum leap in our ability to see the unseen. Its immense gold-coated mirror is not designed to capture visible light, but is a supremely sensitive instrument for detecting infrared radiation, the same faint heat signature that first hinted at the hidden dust. Webb can scan the main belt with a resolution and sensitivity that dwarfs its predecessors, potentially transforming that diffuse infrared glow into a detailed map. It could distinguish between a uniform fog and a structured torus of dust by analyzing subtle variations in warmth across different regions. It might even detect the unique thermal fingerprint of carbon-rich material versus metallic dust, finally answering the question of what this ghostly veil is made of. But Webb is not working alone. Missions like Lucy, currently journeying to study the Trojan asteroids that share Jupiter's orbit, will provide crucial context. By analyzing the composition and history of these primitive asteroids, Lucy will help us understand the violent processes that may have created the hidden belt in the first place. The data it returns will act as a key for interpreting the larger mystery. Every new observation, every byte of data from these advanced platforms brings us closer to a eureka moment. One day, perhaps soon, an astronomer will look at a dataset and see not just noise, but the clear, unmistakable outline of a structure we have only felt in the shadows. It will be the moment a ghost takes form, revealing a lost chapter of our solar system written in dust and gravity. While the James Webb Telescope feels for heat, another observatory listens for whispers in a different language entirely. High in the thin, dry air of the Chilean Atacama Desert, the Atacama Large Millimeter/Submillimeter Array, known as ALMA, is not a single telescope but a forest of 66 individual antennae working in perfect synchrony. This sophisticated instrument does not see light or heat in the conventional sense. Instead, it tunes into the faint radio waves naturally emitted by the coldest objects in the cosmos. Think of the universe as a vast radio station, and every object, no matter how dark or frigid, broadcasts on its own unique frequency. ALMA is the most sensitive radio receiver ever built, capable of picking up the faintest signals from the void. Its speciality is the realm of the profoundly cold, the dust and gas that hovers just a few degrees above absolute zero. This makes it the perfect tool for eavesdropping on the invisible asteroid belt. The fine dust and countless pebbles that make up the hidden structure are incredibly cold, but they are not completely inert. They constantly emit a faint whisper of energy at millimeter and submillimeter wavelengths, a silent hum that is their only cry for attention. ALMA can be pointed toward the main belt and tuned to listen for this specific hum. By combining the signals from all its dishes, it acts as a single, gigantic ear, capable of creating an incredibly detailed map of these radio emissions. This would not be a picture in the way we normally think of one, with shapes and shadows. It would be a data-driven image, a ghostly contour map of density and distribution. A bright spot on ALMA map would not be a reflection of light, but a concentration of this cold, radio-emitting material. It could finally reveal whether the hidden mass is a uniform fog, or if it clumps into dense, narrow rings, or even if it forms that predicted tilted torus. This would be the first direct portrait of the invisible structure, not inferred from its gravity or its warmth, but constructed from its own faint, cold voice. This hidden dust is not a permanent monument, but a fleeting participant in a solar system-wide web. The fine particles that make up the invisible belt are constantly on the move, pushed by a force so gentle it defies our everyday experience, the pressure of sunlight itself. A single photon from the sun carries a minuscule amount of momentum, and when it strikes a tiny dust grain, it gives it a tiny push. Over the immense spans of cosmic time, this constant bombardment acts like a steady, unrelenting breeze. This phenomenon is known as the Poynting-Robertson effect. It does not just push dust outward, it actually causes the particles to slowly spiral inward toward the sun. Think of a runner on a circular track constantly feeling a headwind. To maintain their energy, they must lean inward, tightening their turn. In the same way, as a dust particle loses orbital energy to the pressure of sunlight, its path inevitably decays, drawing it closer and closer to our star's fiery embrace. This means the invisible asteroid belt is not a sealed vault, but a dynamic reservoir continuously feeding material into the inner solar system. So where does all this migrating dust end up? Its final destination is a spectacle you may have already seen without knowing its origin. On a very dark, clear night, far from city lights, you might have noticed a faint, ethereal pillar of light rising from the horizon just after sunset or before sunrise. This soft, triangular glow is not the Milky Way, it is the zodiacal light, often called the false dawn. For centuries, its source was a mystery. We now know it is sunlight scattering off a vast cloud of interplanetary dust that fills the plane of our solar system, a cloud we are essentially inside of. This discovery creates a profound link. The hidden belt between Mars and Jupiter is likely a primary source, a cosmic quarry constantly supplying this immense dust cloud. The fine, dark particles are nudged out of their hiding places by solar radiation. They begin their long, slow spiral sunward, and they join the diffused disk that creates the zodiacal glow. This completes a cosmic cycle. The dust is born from violent collisions in the belt. It migrates across millions of miles of space, and it ultimately contributes to one of the most subtle and beautiful lights in our sky. The invisible structure is not an isolated artifact. It is a beating heart in the solar system's circulatory system, pumping ancient material on a journey that ends only in the fires of the sun. Perhaps our solar system is not a closed family of planets and asteroids, but a cosmic collector. The idea that some of this hidden mass could be captured interstellar objects offers a breathtaking alternative to the local destruction theory. We now know our cosmic neighborhood is not isolated. The arrivals of Oumuamua and Comet Borisov were historic events, the first confirmed visitors from other star systems. These were not objects orbiting our sun, but travelers merely passing through, slingshotting around our star before heading back out into the galactic dark. But what if some of these interstellar wanderers did not just pass by? What if, during the solar system's chaotic youth, a few were snared by the sun's gravity and trapped here permanently? This is not as far-fetched as it sounds. The early solar system was a dense cluster of young stars and planets, all forming from the same nursery. In such a crowded environment, the gravitational pull of our giant planets, especially Jupiter, could have easily acted as a net, capturing rogue objects that drifted too close. These captured interlopers would not have formed here. They would be ancient relics from entirely different stellar systems. Once captured, they would eventually be shepherded by Jupiter's gravity into relatively stable orbits, likely settling into the vast expanse of the main belt. There, they would become permanent, yet nearly invisible, residents. Their composition could be wildly different from the native asteroids. They might be made of exotic ices or strange, dark carbon compounds unknown in our own system. This would explain their profound darkness and their resistance to being seen. A population of such captured objects scattered across the belt would contribute significant mass without reflecting much light at all. Finding even one would be like discovering a library from another star, offering a tangible piece of a world that formed light years away. The hidden mass of the asteroid belt might not be one secret, but many, a collection of cosmic souvenirs gathered over billions of years. This relentless grinding is the engine that sustains the invisible belt. Even today, the main belt is a scene of slow-motion destruction, a process known as a collisional cascade. Imagine two mountains, each the size of a city, drifting through the void at tens of thousands of miles per hour. Their impact is not a gentle bump, but an apocalyptic release of energy, shattering both bodies into countless fragments. But the process does not stop with the creation of boulders. Those boulders themselves continue to collide, breaking down into rocks, then pebbles, and finally into the fine, dark dust that evades our sight. This cascade is a factory that has been operating for billions of years, constantly replenishing the supply of microscopic particles. It transforms the visible rubble of the belt into the invisible veil we can only sense indirectly. Without this ongoing process, the delicate dust would have long ago spiraled into the sun or been blown away by solar radiation. The hidden structure is not a static relic, but a dynamic, breathing entity, its population of fine dust continuously being born from the destruction of its larger parents. This means the ghostly belt we detect today is not the same one that existed a million years ago, nor will it be the same a million years from now. It is a living system, a cosmic ecosystem where creation and destruction are two sides of the same coin, forever feeding the silent cloud that hangs between the worlds. Ultimately, this hidden structure is a direct window into our own creation. The asteroid belt, in its entirety, is a preserved fossil of the protoplanetary disk, that swirling cloud of gas and dust from which every planet was born. By measuring the true, total mass hidden within this zone, both seen and unseen, we are essentially weighing the original building materials set aside for planet formation in this region. This is a critical piece of data, a number that has been missing from our models for decades. Think of it like an archaeologist trying to understand an ancient civilization, but only by studying the grand monuments left behind. Without knowing the size of the quarry that supplied the stone, the story is incomplete. For our solar system, the planets are the monuments, and the asteroid belt is the quarry. Its total mass tells us about the initial density of the disk in this crucial zone between Mars and Jupiter. Was there enough material here to form another Earth-sized planet, or only enough for a smaller Mars-like world? The answer, locked within the gravity of this invisible dust, directly shapes our understanding of how the terrestrial planets, including our own Earth, came to be. The processes that sculpted this belt, from Jupiter's gravitational bullying to the catastrophic shattering of protoplanets, are not unique to our neighborhood. They are universal. By decoding the history written in this dark dust, we gain a template for understanding planet formation across the galaxy, turning this local mystery into a key for unlocking the story of worlds everywhere. Confirming this hidden belt would resonate far beyond astronomy. It serves as a profound and humbling reminder that our maps of the solar system, the very ones we teach in schools and print in textbooks, are still provisional. We have sent probes to the edge of interstellar space, yet we are still uncovering fundamental structures in our own celestial backyard. This discovery would not simply add a new chapter to our science books, it would force us to rewrite the old ones. Entire sections on the mass, composition, and history of the asteroid belt would need revision, transforming our solar system from a seemingly finished portrait into a living, evolving puzzle. This is the true engine of science, not a collection of settled facts, but an endless process of questioning and refinement. It demonstrates that our understanding of the universe is always a work in progress, a draft that is constantly being edited by new evidence. Every time we peel back one layer of the cosmic onion, we find another, more intricate layer waiting beneath, challenging us to look deeper and question everything we thought we knew. You do not need a multi-million-dollar telescope to join this search. The most important tool is your own curiosity. Astronomers are now harnessing the power of the public through citizen science projects, inviting people everywhere to become cosmic detectives. These initiatives allow anyone with an internet connection to sift through the immense flood of data collected by automated sky surveys. Your mission, should you choose to accept it, is to look for the subtle signatures of this ghostly dust. One of the most promising methods involves watching distant stars. Imagine a star shining steadily for millions of years. Now picture an immense, diffuse cloud of dark dust drifting silently through the asteroid belt, passing directly between that star and our telescopes on Earth. The star would not blink out like it does when an asteroid passes. That event is too sharp and quick. Instead, its light would dim by a barely perceptible amount, a faint and gradual fading as the tenuous dust cloud scatters and absorbs a tiny fraction of the starlight. This is the signal you will be trained to find. Projects like these rely on the human brain's incredible ability to recognize patterns that even advanced algorithms can miss. By examining light curves, which are simply graphs of a star's brightness over time, you could spot the telltale dip caused by a hidden dust cloud's transit. Every classification you make, every potential signal you flag, helps professional astronomers narrow their focus. You are not just playing a game, you are contributing to a massive, collaborative filtering process. The data is too vast for any single research team to analyze completely. It requires a global army of observers, each bringing their own focus and perspective to the task. A discovery made by a citizen scientist could be the crucial piece of evidence that finally maps the contours of this invisible structure, proving that the greatest explorations are no longer reserved for a select few, but are a journey we can all share. Our own solar system is not a unique snowflake. When we peer across the galaxy at other stars, we find a common architecture that makes our local mystery feel even more profound. Powerful observatories like the Hubble Space Telescope have not only found thousands of exoplanets, but they have also directly imaged the dusty debris that surrounds these distant suns. We call these structures exobelts, and they are the asteroid belts of other solar systems. The images are breathtaking, revealing vast, brilliant rings of dust and rubble that often dwarf our own main belt in both scale and density. Some of these exobelts contain enough material to build entire planets, shining with an intense infrared glow from countless collisions. Their sheer brilliance tells a story of a far more chaotic and crowded environment than the one we inhabit. This galactic perspective forces a startling question. What if our own hidden belt is not an oddity but the norm? We have always assumed our solar system's asteroid belt was a relatively sparse and calm place. But these distant mirrors suggest that massive, complex debris structures are a standard part of planetary system architecture. The difference might not be that they have belts and we do not, but that we have only just learned how to see our own. Our invisible veil of dust could be the faint, worn-down version of the brilliant rings we see around other stars. Perhaps every mature solar system holds a similar hidden reservoir of fine material, the quiet, dark remainder of its violent youth. The fact that we are only now detecting ours does not mean it is rare. It simply means our technology has finally caught up to a common cosmic truth. Our backyard is not empty, it is simply dressed in camouflage, a silent member of a galactic family of debris disks we are only beginning to understand. This invisible wealth transforms the asteroid belt from a scientific curiosity into a potential economic frontier. The idea of mining the fine dust itself is a practical impossibility, like trying to collect smoke with a butterfly net. The true value lies not in the ghostly veil, but in the roadmap it provides. The hidden mass acts as a giant gravitational signpost, pointing toward the existence of larger, resource-rich parent bodies that have so far eluded our detection. These unseen asteroids, cloaked by the same dark material that makes the dust cloud invisible, could be the sleeping giants of the solar system's economy. They are likely carbonaceous or C-type asteroids, which are the most primitive and chemically rich objects in our cosmic neighborhood. Imagine a mountain floating in space, not made of simple rock, but a composite of water ice, complex organic compounds, and metals. For a future civilization living and working in space, such an object would be a treasure chest. Water is not just for drinking, it is the source of oxygen for astronauts to breathe, and when split into hydrogen and oxygen, the most powerful rocket fuel known. An asteroid rich in water ice becomes a cosmic gas station, a vital waypoint for ships traveling from Earth to the outer planets. Beyond water, these dark asteroids are thought to be laced with platinum, iridium, and other rare Earth elements. On Earth, these metals are incredibly scarce and difficult to mine, but in a single, accessible asteroid, they could exist in quantities that dwarf our entire planetary reserves. Mining them in the microgravity of space would not trigger the same environmental devastation as terrestrial mining, opening the door to a new, off-world industrial revolution. The hunt for this invisible structure, therefore, is not just an academic pursuit. It is the first step in a cosmic prospecting survey, charting the hidden lodes that could one day fuel our journey to the stars. The evidence converges into a single, breathtaking narrative: gravitational tugs on spacecraft and the subtle orbital quirks of asteroids first whispered of unseen mass. The faint infrared glow detected by our most sensitive telescopes then gave that ghost a body, revealing a pervasive warmth from countless cold, dark particles. Supercomputer simulations showed us how such a structure could form and persist, with Jupiter's gravity shepherding fine dust into a stable, hidden configuration while sunlight pressure sculpts its form. All these threads weave together a coherent picture, transforming our understanding of the asteroid belt. We can no longer see it as a collection of lonely rocks set against an empty void. It is a single, dynamic system with two distinct identities. The bright, rocky asteroids we can see are the scattered mountains of this realm. The dark, dusty component is its atmosphere, a vast sea of fine debris that fills the space between them. Both were forged in the same primordial crucible of violence, born from the catastrophic breakup of infant worlds, and then meticulously arranged over billions of years by the relentless gravitational hand of Jupiter. This invisible ocean of dust is not a separate entity, but the very soul of the belt, the missing piece that completes its story and connects its present to its tumultuous birth. This journey began with a simple question, a faint inconsistency in the motion of distant rocks. It has unfolded into a profound scientific mystery, a testament to the relentless human drive to understand the universe. The search for the invisible asteroid belt is science at its very best. It is not about memorizing facts from a textbook, but about following the clues, investigating the anomalies that do not fit our established models. It is a process of looking at the familiar and daring to ask what we might be missing. Every great leap in our understanding starts exactly this way, with a quiet curiosity about a detail that does not quite add up. This hidden structure, once just a ghost in the data, is now a tangible target, its existence supported by the converging evidence of gravity, heat, and sophisticated simulation. Our cosmic backyard is not the quiet, mapped-out neighborhood we once thought. It is a place of hidden currents and unseen architecture, a realm where the past is preserved in a veil of dark dust. The great explorers of the future will not only be those who travel to the stars, but those who continue to look more deeply at what has been in front of us all along. So keep watching the skies and nurturing that sense of wonder, for the next great discovery, the next invisible structure revealed, might be waiting just around the corner.